Welcome to this course on advanced computer networks. Today we'll be starting with the first module of this course, which is in high performance switching and routing. And so here is a sample network where there are three routers. Let's name them as R1, R2 and R3. There are three routers and then 6 computers. There are some IP addresses assigned to these computers and they are shown here, 10.0.1 and something along the lines. And typically a network router has got something called as the routing table. So this we might have studied in our undergraduate course, where the routing table looks something like this. It has got two components. One is the something called destination IP address and port number, and this is the routing table for the router R2. What it means is every entry in this table, if you receive a packet with the destination IP address of 20.0.0.1, this routing table tells this router that you need to forward it to port number 3. That is the meaning of that. And similarly, if you receive a packet with the destination IP address 20.0.0.2, you need to send it to port number 3 and so forth. So such routing tables are there with the every router. It's there with the R1, it's there with the R3 and forth. So depending upon where those destination hosts are connected, so the routing table, because now with respect to R3, where the nodes 10.0.0.1, so that is changing. So probably if I take this route from then to reach 10.0.1, this routing table R3 would have an entry something like this. If you receive a packet with 10.0.1, you need to send it to port number 3. Port number 2, sorry. Port number 2 is the notion of this router R3. So what is port number 2? And the other end, see, the router R2 might have a different port number on the same link. So that's okay. So with respect to that router and what is the routing table, it says based on that the routing decisions are made. So this job of routing is the fundamental job of any router. A router is supposed to do routing, route the packets to corresponding destinations, and that is the primary job. And in addition to that, there are some other additional things that typically routers do. So we will understand what are those decisions. And the objective of this module is, so this seems to be simple. You have a routing table and then you receive a packet and look into the header field of that packet, look at the destination IP address and then send it to one of the output port according to what the routing table actually says. But it is not that simple. What the kind of the question that we ask is, as the link speeds increase, every day, we see that earlier we used to talk relay bandwidth in terms of the kbps, now mbps, now gbps, and several gbps link speed we talk nowadays. So if that is the case, then what is that it takes these routers to handle such kind of the massive traffic in the live network? So they are the kind of questions. So basically these network routers also need to handle such traffic at a very large speed, and we require some algorithms and hardware mechanisms which support handling such a massive amount of the traffic in real time. So that is what is all about high performance switching and the routing. So just to put the things in context, here is the network bandwidth trajectory. So earlier, when the computer networks came into existence way back with ARPANET, people were talking about kbps, and the first network was operating around 54 kbps. Back then it was a very good bandwidth, and then in 1987 people started talking about 1.5 Mbps and the Cisco in 1990 said that they have technology to transmit 155 Mbps in the backbone. And in 2000, people started talking about 2.5 Gbps. I'm talking about the backbone, not the end user bandwidth. And as we speak today in 2022, people are talking about 250 Gbps of trunk speeds. So trunk speeds, these are between the backbone router, one router to another router in the backbone of the internet service provider networks. So that is the typical speed we are talking about. So if you want to handle such a massive amount of the traffic, 250 Gbps, then your network routers and switching elements also need to have capacity to process these packets. Basically, if I want to do the lookup at this speed, there are millions of packets that are coming per second, and can I handle those millions of packets in real time? So if at all, if the answer is yes, then what is that it takes in the routers and switches to do or perform such kind of massive scale operations in the real time? That is the question. So in order to understand how this bandwidth trajectory, increase in the bandwidth trajectory, and also the performance improvements that are required in the network routers and the switches, let's begin with looking at how exactly the internet service providers networks are interconnected, or in other words, how the internet look like in today's world. What is there in the internet, how they are actually interlinked to. If I send up, if I'm sitting here and accessing a site which is located somewhere in the US, what is that, how the routing actually happens, at each router, at each network element, what is that is actually happening, and so if you look at it in context, so you will understand what is the scale of the operations that we are looking at. So, as all know, all of us probably will buy the internet connection from network service providers, and either if I'm an institution subscriber, let's say like IIT Indore, we might go to an internet service provider and buy some kind of the bandwidth, and they provide a lease link connection. Or if I'm a home user, then I might go to again same service provider and then ask the kind of the connection that I get at home and kind of the connection that I have at the institution might be slightly different. But nevertheless, from the service provider's perspective, it is the one network, they have the backbone and they interconnect among other internet service providers. So the question is how these internet service providers themselves are interconnected to each other. So the way internet in today's world look something like this. You have got a hierarchy of internet service providers. At the larger scale, you have something called as the tier 1 ISPs, and there are a bunch of them. So tier 1 ISP, here this is a second similar tier 1 ISP, and the third one here, this is also a tier 1 ISP. And there are routers which are located at the boundary of these networks, and either these tier 1 ISPs themselves are interconnected through a link, or they might go to a third party and then terminate their network links to these third party locations. So for example, in between there is router or this guy, or if there is a third ISP which is again a tier 1 ISP, so he might bring his own link and then terminate into one. So this location where multiple internet service providers are terminating their connection is called as the exchange. This is this is also called internet exchange, where multiple links are actually terminating. And these routers which are sitting at the edge of their network are called as the border routers. So you can think of this as one autonomous system. At the autonomous system boundary, you have got the router. That router is called as the router. And typically these tier 1 ISPs do not provide internet services to the end users, be it the home user or be it the institution subscriber. For both of them, they typically don't provide the service. But what they actually do is, there might be smaller ISPs located within their territory, and to all of them they might provide the license. So there are tier 2 ISPs and multiple of them, so within their geographical area. So the tier 1 ISPs have got connections. They have got something called point of presence. These tier 2 ISPs might actually connect to their point of presence locations and then buy bandwidth. So this could be probably a BSNL network in India, an Airtel network in India, and something like this. These are probably the tier 2 ISPs. They do provide the connectivity to the end users, subscribers, but they themselves buy the connections from bandwidth from the other tier 1 ISPs. And you might have even smaller players located within this area here and there, which are called tier 3 ISPs. Earlier days, or no, even now also, these sometimes the cable network operators also used to provide the internet services. These are typically, they might have presence in one small city, some small districts and all those things. Very limited area they cover. Such internet service providers are called as the tier 3 ISPs. So I might have a connectivity between the tier 1 ISPs are anyway connected either directly or through some internet exchange point, but sometimes the tier 2 ISPs themselves might decide to connect their own network and build their exchange points. So that prevents them from going. If I want to send a traffic from a host which is located in this ISP, in the absence of this peering link, I need to go to this guy and then come to enter into the other network. So if I, on the other hand, if I establish a direct link between these two, then the traffic, I don't have to rely on the higher level internet service providers to route my packets. This is how the internet is actually structured. So if this is the structure of the internet, and look at the scale. This guy might be an AT&T network in the US, and I have some other, maybe a Bharti Airtel or BSNL in India, and I'm talking about the entire network, entire traffic of BSNL or Airtel going to this border router and then going to the AT&T network. So that is the scale. So entire nation's traffic, probably nation's traffic, this router need to handle in real time. It need to process that. So that is the scale. So it requires special, so meaning this router need to be capable of handling those many number of the packets. Now there are, I said that routers need to do this routing operation, that is the consulting the routing table and then making the decision of where to forward that packet. In addition to that, these routers also need to do some other job, maybe the quality of service, maybe the other operations, like if I want to block certain traffic from going, filtering operations and all that, those all into picture. So all these decisions need to happen in real time. So if that is the structure, how do we engineer or build such scalable routers which can perform these operations in the real time? That is the question we want to ask in this part of the course. So before we move forward, I said that tier 1 ISPs usually don't provide the connection to the end users. Here are some handful number of the tier 1 ISPs which are there as we speak in today's. So there are only few of them. So they are having a large geographical presence, probably covering the entire one nation, and then internally they are distributing the bandwidth to the other service providers, tier 2 and tier 3 networks. So here is a sample connecting up one of the internet service provider networks, how their backbone links look like. So whatever you see as a dotted line here, these are called as the point of presence and or an exchange point. And you have whatever you call, this one is the link, and they have scattered links all over the, this is the US network. And through this point of presence key, they actually are providing the connectivity to the other tier 2 service internet service providers. I said that through the exchange points, these internet service providers are connected. In India also we have an exchange point that is called a National Internet Exchange of India. So in short form, this is also called as the NICSI. So in the year 2003, Indian government established this. This is actually a non-profit organization which is mandated to provide the exchange services between the service providers which are located in the India. Meaning, if I am an Airtel subscriber, if I want to access or send a traffic to a BSNL network, I don't have to go to the tier 1 ISP. So within the equation, so this is my BSNL network and this is my Airtel or Jio network. And since BSNL is also connected to this exchange point and Jio is also connected to this exchange point, and so is the Bharti Airtel, and they also terminate. So and all of them together might be buying the bandwidth from tier 1 ISPs, but these BSNL doesn't have to send the traffic to their tier 1 ISP to exchange packets between these networks. So that is this is where the NICSI come into picture. So this exchange point. So the idea is the domestic traffic which is mean from one subscriber within the Indian geography to exchange the traffic between another computer in the same geography. I don't have to send that my traffic to the higher level. Maybe if tier 1 ISP is located in some other, because maybe in European country or let's say in US. So if these guys BSNL and Jio don't know how to talk or exchange the traffic between them, and if a subscriber of the BSNL network has to send a traffic or a packet to another user in the Jio network, all that he need to do now in the absence of this exchange is go to the tier 1 ISP who is located in the US, and then from there you come back and deliver the packet to the Jio network, which is actually a lot of work to do. You distance wise also it is far away, and also it is a costly. There is no need to send or domestic traffic to the external. So that is what they look like. And these are internet service providers are not the only people who are connected to this exchange points. Sometimes there is something called as the CDN. CDN stands for Content Delivery Network. Maybe Google or YouTube. And they have content. YouTube has a content, lot of content, and these guys might develop or put up their own servers and build their own infrastructure, which is looking as similar to that of an internet service provider. There are multiple servers. They have the optical fiber running between those servers. They have routers and all that. They can also come and join these internet exchange points. In fact, in the NICSI network as we speak today, there are CDN network which are also connected to these internet exchange point. So they can also pair their connection to this exchange point and then deliver. So if let's say a subscriber sitting in the Jio network wants to access a content located from a server in this CDN network. So again, the same concept work. I don't have to go to the service provider who is in the USA and traffic going all the way and then coming back to this place and relaying the traffic between these two systems. Geographically, these are closer, and if you have an exchange point between them, then you can actually deliver the content. So that is the role of these exchange points. So in summary, what I wanted to say is these exchange points help to interconnect different internet service providers. On a global level, the tier 1 ISPs are anyway connected either directly through an undersea cable, some other kind of through an internet exchange point, they are able to talk to each other. But on a local level within a country, you might still have the exchange points. They will connect other local tier 2 and tier 3 ISPs also, or sometimes the CDN networks also. So that brings us to the question. So if you take the Indian context as we speak today, how does the internet connectivity to the Indian subcontinent look like? How we are actually connected to the rest of the world as we speak today? So you can see that on the inside there is a bunch of undersea cables terminating at this location. This is the Mumbai area, and on the eastern side you might have the this Chennai. There are a lot of cable terminating going to the east, mainly to the Singapore and Malaysia and other places, and from this location we are actually going to the Europe and US continent, and some of these locations are in Kerala, Thiruvananthapuram and Cochin and all that. These places, whichever are highlighted in the mark, are called as the landing sites where the undersea cable actually terminate, and these are the high capacity, high bandwidth undersea optical fiber cables which connect the entire nation's internet network to the rest of the world. You see, these landing sites are, because I am talking about undersea cable, they actually the presence of these and these cables actually terminate at the places where you see the sea coast. So here is a picture which is actually of them, how the cables, these undersea cables are down. On the left hand side the diagram, you see a set of men who are actually laying such cable, and on the right hand side we see is a ship which is actually carrying that undersea cable. They are doing the laying operation, and here is the bottom tool is actually how the cable look like, and the typical machine how actually that undersea cable is actually laid. So these undersea cables are now the backbone or the prominent sources of data exchange. So if there is a fiber cut, this undersea cable is cut, then probably a part of the entire internet, one of the internet service providers network might be affected. So it requires a very high availability and maintenance, so that this cable is never you put, even in the undersea cable also, every 2 kilometers or miles you put repeaters, because the signal deteriorates and then you need to maintain that cable. So that's why it becomes essential to see that how much traffic is being exchanged between these two service providers. Based on that, whether it makes sense to lay down a cable between or connect these two internet service providers directly or not, or going through an intermediate exchange point is a better option or not. That's the business need to make. So the backbone, these undersea cables that are talking about, there are a bunch of standards over a period the people have developed how much capacity of the bandwidth they can offer. So right from something called as the OC1 was able to provide 51.84 Mbps of the backbone data, meaning that if you lay one cable of the type OC1, the maximum bandwidth that you get is about 51.84 Mbps. Similarly, the standard called OC3, that will give you around 155.52 Mbps of the data and so forth. You can see that as the time passed and the developments in the optical fiber technology brought several Gbps of the or Mbps of the bandwidth to the backbone. So a technology called OC3072 is now able to provide you 159.252 Gbps of the bandwidth at the backbone level. So that's actually a lot of bandwidth. So using this kind of the bandwidth, now if I want to design a router which is doing the lookup operation and routing the packets, how do we actually design such a massive scalable router? What is that goes inside such routers, which is high level, high availability, operational 24/7, able to handle large amount of the traffic and forth. So the routers in this case, I said the border routers are one type of the routers, but there are other type of the routers as well. So the border routers are sitting at the boundary between two networks, two autonomous systems. One entire internet service provider also you can think of that as an autonomous system, and in between these there are many routers. They are also interconnected in some fashion, something like this, and this guy might be connected to the another border router and something like this. So the router which is here are all the border routers, but the routers which are inside the backbone or the internet service internal network, which are not directly providing the service to the end users, meaning if I am home subscribers, my connection from my home to the server network does not terminate in these routers. Such routers are called as the core routers. And again, core routers are also need to handle large quantum of the traffic. But on the other hand, I might take a connection from this router and then bring it to the another router, and from where multiple number of the users or subscribers are connected to. So such routers are called as the distribution routers or the service provider service routers, where the end users typically connect to these routers. So be it my home subscriber or the institutional subscriber like IIT Indore. So all these subscribers actually come and terminate at this router. That is called as the distribution router or the service router. And the reason why we are making this differentiation is the kind of the operations that are done if you are a distribution router or an edge router or a core router or a border router, they are different. They are meant to handle different kind of the agents. So the kind of the filtering, lookup and all the kind of operations that I do at an edge router is completely different than what the core router is supposed to do. So in a nutshell, core router and border routers are mean for core router is typically need to just do the lookup operation as quickly as possible and then send the traffic to the or packet to the next router so that the packets can actually go through. So if a packet comes here, I don't do much of the operation here, just find out quickly what is the next hop where I need to send this packet and just send it. So because these routers need to handle a large quantum of the traffic. But on the other hand, this edge router can do some other end of the operations like the filtering, the quality of service, the traffic policing, whom to, how much data, who is using, keeping the account of the bandwidth consumption of the end users, and all these things can be done at the edge routers. So the point is, depending upon where exactly these routers are located and what functions they are supposed to do, based on that I need to customize that router's operations. So this is a core router, is going to sit in the backbone, it need to do the lookup operations quite quickly and then handle massive amount of the traffic. So I engineer that router for that. This is an edge router connecting the end users. I require accounting information. I require policing operation. Policing means how much bandwidth who is using, what kind of applications is using. If I am, let's say, I'm a home user, I have a 10 Mbps connectivity at my home. But if I send a traffic more than 10 Mbps, then the service providers usually throttle that. Okay, you are sending too much of traffic, but you are allowed to send only 10 Mbps. Now, I am not able to handle this excess traffic. You reduce it. Basically, they drop the packets then and there itself at the edge router and then transmit the only 10 Mbps connecting traffic from that router to the next router. So these kind of operations are done at the edge. So that customization is actually done in the router. So, but as the days pass on, the network capacity, the bandwidth available at the backbone keeps on increasing, and more number of the subscribers join the network. As the internet subscribers increases, as the network bandwidth increases, it put more pressure on the backbone routers and the baud-wire routers to do the things quickly. So in order to understand the scale of the operation that is required at a typical border and the core router, I took this diagram. This is a set of something called as the prefixes. The IP address that we saw in this example in the first slide. So this is a complete IP address is there, but it is not necessary that you need to have the complete IP address, but there is something like this can also be there. Anything that is destined for 30.0.0, so star doesn't matter whether it is 1 or 2, you still need to use the port number 4, that is what it says. So if you recollect the CIDR operations classless, so the way the routers handle this is, they don't have the complete IP address of the every destination stored in their routing tables. You merge several of the IP addresses, get something called as the prefix. I might have a prefix for something like the 10.10 something star, I might have 20.15 star, something like this. Anything that is any IP address, so let's say I have IP address 10.15.1.1. So this precisely falls under this prefix, and if it is telling you to route to the port number 10, send it to port number 10. So I get such a kind of the IP address, complete IP address, but I am able to send that to. So I forward this IP address. If a packet comes to any of the one of the router having this particular IP address, I am going to forward that using consulting these prefixes that are available to port number 10. So this is called as the prefix structure, and the routers typically keep such prefixes, not the complete IP address. You might have one or a set of the complete IP addresses, but a few others which are in this prefix format. This is by aggregating some of these IP addresses, such prefixes are actually generated. And what you see on the left hand side is number of the prefixes that are available with a typical backbone router, as seen by this is one of the router that was located in Japan, and on a particular date on the 16th of 8, 2022, there were in that router 9,29,299 prefixes were there. These are distinct prefixes, something like 10.10 star and 20.15 star, something like that. And these prefixes, distinct prefixes, sometimes are aggregated and then to minimize the number of entries in the routing table. So on the rightmost column, what you see is the CIDR aggregated. If I am able to merge two prefixes and get one, so that will bring my total number of the prefixes inside the routing table. So the smaller the number of the prefixes you have, the better it is, because given one packet and you pick up the IP address, destination IP address from that packet, and then you go and consult that table whether prefix number 1 is matching, prefix number 2 is matching, prefix number 3, and so forth up to n. So larger the number of the prefixes you have, the more amount of work you need to do the search, because the lookup operation. And so that's why the aggregation actually help. Keeping them to a smaller number of the entries actually give you performance improvements. So as you can see, over a period of time from 16th to 23rd date, so see from 9,29,299 on the 16th August, so you see 9,30,468 as of 23rd date 2022. So what it means is the number of the prefixes over a period of time is going to increase. So the larger the number of entries, this increased number of the prefixes will put pressure on the router. So as the time passes, you actually need to handle larger IP tables, larger routing tables, and more amount of the searching that you need to do. So that's going to be actually a complex thing to do. How do you actually handle such things? We know that bandwidth is going to increase. We know that prefixes are going to increase over a period of time. So actually handle such things. So we need algorithms which can actually do this for us. So any typical router that you think of, there are two operations a router typically does. One is called as the data path operation. So data path operation is basically you are given a routing table, look at that routing table, and packets are coming on your interface, pick up those packets, go to your routing table, and then make forwarding decisions. These forwarding decisions need to be quickly made. And on the second operation, we have something called as a control plane operation, where in the control plane operations, we construct the routing table. Whatever the routing table we constructed, that we used to do the operations in the real time. But in the background, I used to keep on updating my links. New people are joining, links are breaking, something is happening. Topology changing, so I keep learning what are happening, what things that are happening inside my network, and keep updating that routing table. And that is typically done with a bunch of routing table. So we might study these algorithms like RIP, OSPF, and BGP. These algorithms bring that status information of the links and connectivity between the routers. You aggregate that and construct that routing table. So this operation is called as the control plane operation. So the control plane operation is not real time. Constructing the routing table is not real time, but on the other hand, forwarding the packets to the next hop need to be done in real time, because large amount of the packets are coming.